Hello everyone, welcome back to my channel. My name is Dr. Mohit Sharma and in this video we will see the implementation of Actor-Critic method in Python. So let's get started. So as we know that in reinforcement learning, we have an agent which interacts with the environment to get the maximum rewards possible. Okay. So let's say at a particular time t, okay, the agent is in a particular state S, okay, it takes an action from that state AT, it gets some reward, okay, RT, and then because of that action it gets transferred to the next state which is ST plus 1. Okay, so what is our main objective in this? Our main objective is to make the agent learn to find the action which gives it the maximum cumulative reward. Okay, so maximum cumulative reward means for all the upcoming states the accumulated reward should be higher. Okay, so that accumulated reward is given by this, which is the expected value of summation through all the time steps, and this is the gamma to the power t, and r is our reward function. Okay, and gamma is our discount factor between 0 to 1. So if you are not aware of all these quantities, then please look into my previous video where I have explained it in depth. So now in this actor-critic method, we have two neural networks, one for the actor and one for the critic. Okay, so the actor tries to learn the policy, which means the actor tries to understand which action is more beneficial at a particular state depending on the neural network parameters which are given by theta. Okay, so it wants to understand a probability distribution of over all the actions given a particular state. Okay, so let's say this is our actor neural network in which we are passing through an state. Okay, and after passing through this neural network it will give us some actions. Okay, so the probability of all the actions are different. Okay, so it wants to learn the probability distribution which will give us the maximum probability of an action which gives us the maximum reward. Okay, and the critic is estimating that action, okay, the choice of that action in that particular state by predicting some q value. Q value is the quality value. Okay, so we will see this how it happens. Okay, so the main components that we have is that we have a policy gradient method in which we try to maximize the probability of getting the action which gives us maximum cumulative reward, okay, which is given by this, right? And here at is the advantage function. Advantage function means if you take the average of all your actions, okay, let's say the average of all your actions which gives you reward, let's say it is reward is 0, okay, and you choose the action which gives you reward greater than 0. Okay, so your reward is greater than average reward. So in that case, your advantage is positive. So if your reward is less than the average reward of all the actions, then your advantage is negative. Okay, and the predicted value is the Q value, which critic neural network predicts. So it is basically R plus gamma value function for the next state. Okay, so R is the immediate reward and value function is the value of the next state. Okay, so we have loss function for both critic and for actor. Okay, and now we will see how to implement this and implement all these formulas in Python using the PyTorch library. Okay, so now first we need to import some libraries. So let's first import gym library. Okay, gym is basically to call the environment. Okay, and then we have to import this numpy library, import numpy. Okay, and then for PyTorch we also need PyTorch library, import torch. Okay, then we have to import the neural network from torch, import torch dot nn as nn. Then we have to import the optimizer, so import torch dot optim as optimizer. Okay, and then we have to import function torch dot nn dot functional as f. Okay, and then so we have imported some libraries for gym, numpy, and pytorch. Okay, now we have to set the hyperparameters. Okay, so first we need this gamma. So gamma, let's take it 0.99. Okay, and then we need learning rate for the model. Learning rate, let's say it is 0.002. Okay, and then we have to mention how many hidden state we need. Hidden states, or you can say hidden size, whatever you can say, which is 128. Okay, so 128 is a number of neurons, and then we need maximum episodes. Let's say it is 5000. Okay, and then in each episode how many steps we need to take. So let's say the maximum number of steps that it can have in one episode is also 500. Okay, and we have to also fetch the environment. So let's say the environment name, we are fetching CartPole environment. Okay, so there are several environments are there in gym library. You can check in the documentation. CartPole. Okay, so now we have done with our hyperparameters, and now we have to uh, write the actor-critic neural network. Actor-critic network. Okay, so we will not define two separate networks. We will only work with one network, which can produce all these values, which can give you actions as well as the Q value. Okay, so we are sharing the weights between two neural networks. So let us define the class. So class for actor-critic. Okay, and then dot module. Now we have to write the initial state dimensions and action dimensions and hidden sizes. Okay, so self comma state dimension, action dimension, and hidden size. These three quantities we need. Okay, then we have to also write this super actor critic comma self dot edit. Okay, and now we have to mention about the linear layers. How many linear layers we have? So it is self dot fc1 is equal to nn dot. So this is how we import the linear layer in PyTorch. So we have to mention how many state dimensions we have, which we are passing through this first linear layer. So state dimension and what is the size of the hidden layer. Okay, and then self dot fc2, the first hidden layer. Now it will take the hidden size, which is 128, and it will also pass it to another hidden layer with the same size, hidden size. Okay, and then we have to get the output for the actor. Okay, we have to get two outputs, one for the actor, one for the critic. So this, up to this point, it is general for both. Okay, so the actor output self dot actor is nn dot linear. So basically it will have the hidden sizes as input, and it will output the action dimension. Okay, the number of actions we have in this environment. And similarly for the critic, it will also take the hidden size as input, and then it will only give one output, which is this 2 value. Okay, so now we have to set up the logic. So how will the forward pass happen? So define forward self comma x. Okay, and then f dot value, we will just pass this input to the first layer and take the value, and then that output that we will get, it will again, we will pass it to the second linear layer. Okay, and then apply the value activation function. So self dot fc2 x. Okay, and then we will have action probabilities. Okay, so action probabilities are given by the softmax function. Okay, so because we have more than two actions, so softmax, and then self dot actor, we will pass this x to this actor layer, and then it will take a softmax of it. Okay, and then the state value, I mean the this function v is given by state value by the critic neural network. So it is self dot critic. Okay, and then we will just return these two things: action probabilities and state value. Okay, so we have set up our neural network for actor-critic method, and now we have to run the training loop. Training loop. Okay, so up to this point we have not set up the environment. So let us set up the environment first. Environment is gym dot make the name of the environment, which is env. Okay, and then we have to get the state dimensions, how many state dimensions we have from this environment. So it can be fetched out from env dot observation space dot shape. Okay, and then we also have to find how many actions we have. So action dimension equal to this env dot action space dot n. Okay, and now we have to set up our model architecture. So model is basically given by Actor-Critic. Okay, and it has three inputs: state dimension, action dimension, and hidden size. So state dimension, action dimension, and hidden size. Okay, so with it we also need to specify the optimizer. So optimizer is optim dot, we are using Atom optimizer. Okay, and we have to pass the model parameters inside it. Model dot parameters. Okay, and we also have to specify the learning rate. So learning rate is this. Okay, so critic, state dimension, action dimension, hidden size. So yeah guys, I have not written it properly. It should be underscore underscore unit. So here also. Okay, so let's run it again. Yeah. Okay, so now we have to run the loop. This should be training. Okay guys, so we have to first store the rewards that we will get after each episode. Okay, so let us create a list. So episode rewards. So we are just creating an empty list for the rewards. Okay, and then we will run a for loop for all the rewards. Okay, for all the episodes. So for each episode in range, the maximum episodes that we have is 500. So max episodes. Okay, and then in the beginning of each episode we will reset our state. So state will be reset, okay, to its default value, and since we are using PyTorch, so we have to write the state accordingly. So state will be torch dot flow tensor state, okay, on space. So guys, this will do nothing, but this will only rewrite your state for PyTorch calculation. Okay. So if you will not do this, then you will get the error. And then for this particular episode, the reward is 0 currently, right? And we have to have this actions output, okay? And we have to have these values and rewards for each step. So we need three quantities. So actions will be given by the log probabilities, and then values, and then rewards. Okay. So we will create three empty lists within this particular episode. Now, within this episode, the agent will can take at most 500 steps. Okay. So we have to run the loop up to 500 steps. So for step in range max steps, okay, at each state the model will get the action probability, what action it will take in that particular state, okay, and what is the value of that state. I mean, how good is that state is determined by the value of the state. So we have two outputs. First is action probabilities and second is the value, okay, for the given state, okay. And then using this categorical method, it will give us the distribution of the sections, okay. And then we from that distribution we will just take out the random sample, okay. And now based on that particular action that we will take, okay, we have to calculate its log probability. So log probability of that particular action is given by this distribution dot log probability of that particular action, okay. So then after taking a particular action it will go to the next state. So our next state reward, whether it is terminated or not, and two other quantities that we noted for this particular task is given by the env dot step, okay, action. So when you take any action it will give you the next state, reward, and whether the episode is terminated or not, okay. So this is truncated, okay. So if any of them is true, let's say if done is either terminated or truncated, okay, so then we will get done equal to true, okay. And similarly for our next state also we have to write it according to our PyTorch format. So it is torch dot flow tensor next state dot unsqueeze 0. Okay, and now whatever reward you will get in that particular step, you have to accumulate all the rewards within that episode. So your episode reward is plus equal to reward. Okay, and whatever the log probabilities that you will get for each action that you will take in different states. So that also you have to store somewhere in this log probabilities. So log probabilities dot append, okay, log prob, and similarly the values append value dot space, okay, and then also the reward. Okay, and then your next state will be your current state. So your state is equal to your next state. Okay, and if it is done, if done is true, then we will put a break. Okay, okay. So now let us compute our returns. Okay, so let's say our returns are just an empty list. Okay, initially the reward that we have is 0. Okay, and out of all the list of rewards that we have saved just now, rewards dot append reward. So by using this, we will calculate the discounted return. So discounted return is calculated in this way. For R in rewards. Okay. So we will start from the end. Okay. Why we will do this? It will be just clear to you. And then we have to just, so in this code, what is happening is that you are starting from the reward that is at the end. Suppose you have a reward 1, 2, 3. Okay. This is in the state 1, state 2, state 3. Okay. In three different future states, you have these rewards. Okay. So now this gamma will multiply it recursively with the reward that you will get at the end. Okay. So let's say, let us take an example. Let's say I just give it different name, x equal to these rewards 1, 2, 3. Okay, and then I just run this same loop. for this list x. Okay, let us also say this is a different list x1. Okay, so now let us see what is our x1. So x1 is 2.7, 1.79 minus 2 point minus 0.28. So you can see that it is giving more weightage to this immediate reward than less weightage to its future reward. Okay, so same method we are applying here, that it will give more weightage to its immediate reward. Okay, so that is how it is written. Okay, so now we have to normalize these returns. Okay, for better and smooth training. So returns are equal to, we will just normalize it. So returns minus its mean value, returns dot mean divided by the standard deviation, returns dot std plus some small number, let's say 1 e to 10 to the power minus 8. Okay, so now we are left with computing the loss function. Okay, so the loss, we have to first define the losses that we have. So we have actor loss and we have critic loss. Okay, so let us create two empty lists, or let us uh, put them equal to 0 initially. Okay, and then for all the log probabilities, values and rewards that we have generated till now, so that we will, so based on that we will just calculate the actor loss and critic loss. So first, for all the log probabilities and values and log prob value and reward, in, we will just get a zip for log probabilities, values and returns. So it will create a zip of all of them, okay, sequentially, and then it will calculate the advantage first. So advantage, which is equal to your reward that you have obtained minus the value of that particular state. So value dot item. Okay, and then you have to calculate the actor loss. So actor loss depends on this advantage. Actor loss is equal to minus log probability times advantage. So just remember that this we are doing for each state. Okay, we are not just calculating it for all of them combined. We are doing it for each and every state. So this log probability is for each and every state. Okay, and then the critic loss. So this should be plus. The critic loss is r minus value whole square. Okay, so now we will just do the same thing for actor loss as well. We will just take the average and critic loss also. Okay. So after getting actor loss and critic loss, we just have to set our gradient equal to 0. So this is one such thing that we have to do in PyTorch. So let us first set our gradients equal to 0, optimizer.0 grad, and then we have to calculate the total loss. Total loss is combined of actor loss and critic loss. So total loss is equal to actor loss and critic loss. Okay. Then we have to do, after calculating the total loss, we have to do the back propagation. So total loss dot back. It's very simple in PyTorch, just this backward. So you just need to do this total loss dot backward, and that's it. And to update the weights, you just have to do optimizer dot step. Okay. So we have done most of the code, and then we have to also for each episode we have to store the episode rewards. So episode rewards dot append episode reward. Okay. So now we have to print. I mean, how much rewards we are getting after certain episodes. So let's say we will just print after 50 episodes because we are running it up to 500 episodes. Okay. So if episode divided by 50 gives us 0 reminder, then we have to get the average reward for those 50. So average reward is given by np dot mean episode rewards of 50. Okay, and that we have to print episode, and then you have to print average reward. Okay, up to second decimal place. Okay, so let us run this cell. So as you can see, it is training now. So for episode 0 the reward is 18, then the average reward is improving. For episode 200 it is 148, and for episode 250 it is 209, and it is going to 267. So as you can see that it is improving. So the maximum reward has reached up to 431, and yeah. So the training is done. So now we just need to do the visualization, how the rewards are improving with episodes. So for that, let's import this matplotlib library. Import matplotlib dot pyplot as plt. Okay. Then we have to plot the episode rewards. Okay, so plt dot plot episode rewards, where your x label is episodes and your y label is reward. Okay, then plt dot show. So you can see that rewards are increasing. It is starting from 0, and at episodes 500 the rewards are increasing. Okay, so it is going quite smooth. There are quite oscillations as well in this graph, but it is getting trained. Okay, so if you will run it for more episodes, then these oscillations will remove. Okay, so now let us do some testing for this trained model. Okay, so we need to define a testing function. So let's say define test actor critic. Okay, and we have to pass it on the model and the number of episodes also. Let's say episodes are 5. Okay, and we are not rendering it, so keep it false. Okay, then we have to mention the environment. So environment is gym.make env. Okay, so yeah, that's it. And then we have to write the for loop, 4 episodes again. So 4 episodes in range, these 5 episodes. Okay, then again state has to be reset, env dot reset, and then state will be written in the torch format, torch dot float tensor, and we have to pass the state. Okay, unsqueeze 0, and then the total reward initially is 0. Okay, then initially the done is false. So while not done, okay, and since we are doing the testing, so we don't want to do the grid updates. So with torch dot no grid, we will not do any updates. Okay, in the model parameters, we have to get the action probabilities. Model, okay, state, and then we have to get the action which has the maximum probability, okay, not from the sample. So torch dot argmax, action probabilities with dimension -1 dot item. Okay, so now the next state is, and reward, whether it is terminated or truncated, is given by the env dot step action. Okay, So done is decided by whether it is uh, terminated or truncated. Okay, and then we have to accumulate the total rewards. So total reward is equal to plus equal to reward. Okay, and the state will be equal to the next state. So we can write it like this: torch dot float tensor next state unsqueeze. Okay, and then we just need to print. So these are the test episodes. Okay, episode plus one because we are starting from zero, and total reward. Okay, and then we have to close this environment. AMB dot close. Okay, so now we just need to run this test actor critic. We are passing the model episodes. We are giving 5. Okay, and render equal to false. So this saying got an unexpected keyword episodes. Okay, so there is a typo here. It is episodes. So yeah, as you can see that we have quite decent rewards from 301 to 409. So it has almost learned the pattern. Okay, so the maximum reward that we have obtained during training is 431. So it is not bad as compared to the training rewards. So yeah, guys, this is how we can implement this actor-critic method in Python. Yeah, so guys, if you like this video, then please hit the like button and please subscribe to my channel and please share with your friends. Okay, so we will come up with more such videos in the future. Okay, so goodbye.